So I have a friend who works in the service industry. He's a waiter at one of the restaurants, and whenever I go out to eat, I just usually take him with me, and I let him deal with all the ordering, talking to the person who's serving the tables and everything. And our food usually comes the fastest. Do you know why? Because it's a server to server communication. Okay, welcome to second week of Coding Interview Weekly. And if you're wondering what this is all about, you can go and check out this website. So you'll have, apart from the introduction and everything, I also talk about it has a collection of the previous weeks as well as some study material for each of the discussions that I do in videos. Then there are some follow-up articles that you can read and so on. So do check it out. Okay, enough self-promotion. Let's jump to the problem. So for this week, we had this problem, or in fact, the previous week, we had this problem where you have n objects, and each object has a certain weight and a value, and you're trying to optimize by choosing a subset of these objects such that the sum of the values is as much as possible with a given constraint on the weight. So you can't choose all of them. You have to choose a subset because you have constraints on the weights. Now, this sounds like a very typical knapsack problem. Every computer science student must have heard of that. And we all know we have a typical dynamic programming solution. So in an interview, it's okay to mention that you know this problem already and you know about the DP solution and all. But the twist with this problem is that the weight. Okay, before that, you may mention, I would, as an interviewer, I would ask you what is the time complexity, and if you already know this problem, knapsack problem. So the time complexity in that case is number of objects multiplied with the sum of the weights, which in this case is order n. So we have an order of n squared solution using dynamic programming. And after that, I won't talk about it. I would say, okay, we want to do better. We want to do better than subquadratic. We want to do subquadratic. And then the candidate has to think in that direction. So there are some basic insights that you need uh, before you can make progress on the problem. So one thing you can do is basically separate the objects by their weights. And let's say you now have these two arrays, A1, A2, AN, B1, B2, BN. Uh, we have separated them by the weights, and you have these two arrays now. So one basic observation, which is a greedy observation, it goes that I would choose a prefix of this array and a prefix of this array in my optimal solution. Now, how do you reason with that? Like it can be any prefix. We are not saying anything about the length of these prefixes for now, but we are saying that it will always be a prefix. And the greedy argument here is that, okay, assuming that these arrays are sorted in decreasing values. So the greedy argument is this: I'll sort them in decreasing values and choose the first, some of them. Now, how do you prove that? How do you say why is that optimal? So for proving greedy algorithms, okay, greedy algorithms are very tricky like that. You can come up with them very easily, but it's really hard to prove them. So we'll talk about two major techniques that you use for proving greedy algorithms. The first one is greedy stays ahead. And as the name suggests, it goes like this. In any greedy algorithm, you have n steps that you are gonna perform, right? If you can say for all of these steps that the step that I took at ith number, you have to show that was an optimal choice. How do you do that? You say that if I would have instead taken another step, let's say s prime, it would have landed me in a similar or worse situation. So once you have proved that, you have shown that all of your steps are leading you in the optimal direction. So in this example, where we are choosing a prefix of this non-increasing array, how do we apply this greedy stays ahead argument? We say, okay, at the ith step, let's say I chose AI. I am saying if I would not have chosen AI, I would have chosen something which was remaining from the array, right? Let's say instead I chose AJ. Now, since AJ is less than or equal to AI, choosing AJ will only lead you to a similar or worse situation. And hence, you have shown that the greedy step that you took is the right one. And this this typically applies to many of the greedy algorithms. You can try proving. Okay, think of this problem. You have a string A, and you're trying to find the smallest prefix of string A that contains string B as a subsequence. Now you will come up with a greedy algorithm and try to prove it. I'm not going to go into this right now. Now this is the greedy stays ahead argument. There's another technique which we'll talk about later. Okay, so armed with the insight that you're going to choose a prefix, how do we use it to our advantage? It's like this. How many prefixes of array A exist? Well, it's order of n. So if there was a way for us to calculate the optimal answer for a given calculate the answer for a given prefix of A, we can do we can basically evaluate every prefix of A, and then corresponding to each of the prefix, we'll find the answer and then take a maximum of all of those, right? We are covering all cases essentially. So we have order n prefixes. So let's say you chose this prefix of length I. So the weight that you're left with is k minus I, right? Now, how much will the prefix from B bring the value for k minus I weight? Since every object has weight 2, you will choose a prefix of this length from array B. Now, how do you very quickly calculate the sum of values, sum of the prefix of length k minus I by 2 from array B? So for that, we can do simple pre-calculations. So calculating a prefix of an array is basically order of n. You basically traverse through array step by step and use the prefix sum that you have calculated in the previous step and just add it to your current value. And that's a very standard order n algorithm for calculating prefix sums. So in this scenario, we basically, this solution is pretty straightforward, right? It actually does not even depend on whether weights are generalized or not, like whether weights are 1 or 2. They can work, this can work for all generalized weights, and the time complexity is also pretty good. It's just order n, right? Actually, you have to sort the arrays as well if they are already not sorted. So that's around, overall, it will be order of n log n. Cool. So what's the follow-up now? If candidate has gone in this direction, like it's a rather straightforward algorithm. So maybe to make the implementation a little bit complex, I would say something like, what if there are three distinct weights? So you have another weight here and another array, C1, C2, Cn. What do you do in this case? Again, you can apply the prefix the prefix observation. You'll choose another prefix from this array, and now you can fix two prefixes and let's say you fix the prefix length for A and prefix length of B. Now you can figure out, okay, what's the prefix length for C gonna be? So you have a total of order of n square operations in this case, because you're fixing the prefix length from A and B. So those are like n square, total of n square, different options. Uh, Yeah, if candidate comes up with this, that's pretty good. We'll usually go to implementation. Uh, but there's another approach here, which is again goes into the greedy direction. It's much more complex, but for this exercise, it's great. Like we should discuss that. So some candidates they know knapsack already, right? And they know that knapsack problems have this approximate solution where you sort all the objects by the ratio of value versus weight in decreasing order, and you choose a prefix of this ordering you have generated. And we typically know that this does not work for this greedy algorithm, does not work for generalized weights, for like any number of distinct weights that you can have in your input. But maybe this one is special, right? Because we only have two distinct weights, one and two. So why don't we give it a try? So let's say you sorted all your objects by this ratio in decreasing order, and you ended up with something like this: A1, A2, B1 by 2, blah blah blah, BK by 2, blah 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 blah, right? You have some A's here and some A's here as well, and so on, right? And now you're saying I'm going to choose a prefix of this. What could happen really? When you start iterating over this, you may run out of you may run out of the total weight. And let's say you if it's a perfect fit, then that's great. What I mean by perfect fit is that when you end up choosing this object, you are remaining with you have zero remaining weight with you. That's great. In this case, this is one option, right? This is one of the cases. The other scenario is if you have one weight remaining. Actually, the last object could also be one of the values from array A, but we will talk about that case separately. If you're remaining with weight 1, you have multiple options. You won't leave it, right? If you have one of the A's remaining in the rest of the array, you will pick up the most valuable one by greedy argument. The other option is you choose a remaining B, but for that you have to sacrifice one of the A's that you have chosen behind, right? And this covers all the cases basically. So this is one of the greedy algorithms you can propose, but the tricky part is proving it. It's always really hard to prove greedy algorithms, especially like complex ones like these. Uh, so I'm gonna start proving it with one of the cases. Okay, yeah. Let's talk about the other way of proving greedy algorithms, which is gonna be useful here. This one is called, this one is basically exchange argument. Yeah, that's what it's called. And the name is slightly explains what it is about, but I'll go into more detail. So exchange argument goes like this. You take your greedy solution and you compare it with an optimal solution. Now, in a greedy solution, we have a prefix of this array. Let's assume that it's a very simple case where everything fits and we have an exact prefix that we have chosen of this array. Let's try to prove this case. In an optimal solution, you may be choosing some arbitrary subarrays of this, right? Like you won't choose this element here, you won't choose all these elements here, and you won't choose all these elements here in the optimal solution. Let's assume that's the case. So what exchange argument does is it tries to find the first spot where your solution will differ from an optimal solution and shows that if I were to exchange my choice with some choice down the line, I won't end up in a better solution, in a better solution. Yeah, exactly. So let's try to apply that argument here. Let me get rid of this stuff. So we know that it's an exact fit. If it's an exact fit and the last element you chose was from from the last element that you, yes. Okay, hold on. Yes. Let's say B of K, let's say at this step, the optimal solution does not choose this object. Like optimal solution will choose all objects up to this step, but not choose this one. And so we'll try to make an argument by swapping this one with some other objects from the remaining array, right? Because optimal solution also chooses something from here and show that it's not optimal to do that. So this object can either be a B, either from array B or from array A. If it's from array A, if you get rid of this, you have one remaining bit. Then obviously you can't choose an A from the remaining array, which gives you a better solution, right? Because they're already sorted in decreasing order. So the other case to prove is that this object chosen is from array B. So we are saying we are going to replace BK, which takes away 2, with two objects, and like the two others can only be from array A, right? Again, you won't choose BL by 2, which is here, because it's obviously worse than BK. So the condition is this: BK by 2 is greater than or equal to AJ is greater than or equal to AI. Let's say you're trying to replace BK with AJ and AI. Now, in the optimal solution, uh, when would we replace BK with AJ and AI? We would do that if BK is less than AJ plus AI, right? The contribution that B brings is less than AI plus AJ. Now, can this ever happen? Actually not, right? Because BK is already greater than twice of these two integers. So there's no way you can sum up these two integers and end up with a number which is less than BK. And hence we have shown that we'll always choose BK. And this is actually an argument essentially. Now, actually, the proof is not complete, right? If you remember, we talked about if you had one remaining object, we did a bunch of other stuff. So this has a lot of corner cases, and usually in an interview, we won't go into the rigorous proof of greedy arguments. But if you're able to apply some of these intuitive arguments, like exchange argument or greedy stays ahead, I think that's really good enough. As long as you know some of these techniques and do a rigorous proof. And if you're really smart, go ahead, do it. I mean, I would really enjoy that. Now, let's say the candidate does this. I'll be first of all really impressed if somebody is able to do this in an interview. It means they really know the theory. Now, follow-up that I ask is, let's say these weights were not 1 and 2, but generalized weights like W1 and W2. Then how do you reason about that? And again, they have to modify their proof a little bit to see if it works. I mean, it's not very trivial to say that it works, so let's see if it works. So in this case, what would happen is, let's assume that W1 is greater than W2. Actually, let's say, W1 is less than W2. So what could happen is you can replace BK with more than, like by 5 different values actually, right? You can replace BK with W2 by W1 floor of these many AIs. So let's say W2 by W1 is 3 in this case. So you can replace it with 3 AIs. So we say by W2 is greater than or equal to A1 by W1 greater than or equal to A2 by W1 greater than A3 by W1. Now we are trying to prove that BK is greater than A1 plus A2 plus A3. Now this is not trivial to prove uh, for generalized W1 and W2 at least. But I think it holds because let's say you transfer this W2 here, right? And in this case, if it's 3, we are saying BK is greater than 3A1, 3A2, 3A3. And if we sum them up, uh, it will still be greater than, it will still be less than BK because BK is at least thrice of that. So this is again slightly tricky, and but it should still work. You'll have to handle much more cases here. Like you end up with 0, 1, or let's say W1 minus 1 objects. So yeah, I don't even know if it works. Okay, I'll leave that as an exercise. Isn't that what professors do when they can't explain stuff? Okay, I'll try to prove it. Let's see if it works. But at least this inequality holds, right? So, but the algorithm is not complete yet because of these corner cases that were there for 1 and 2 weights. So, in terms of the time complexity of this approach, we are sorting all the values again and then just iterating over the prefixes. So it's still order of n log n. Yeah. So that's about greedy algorithms. It's much more theoretical, and I'm never confident about greedy algorithms that I come up with unless they're really, really obvious. So in terms of exercise, I'm gonna post them on lalitkundu.com, and I'm also gonna post the next week's coming week's problem on that. And feel free to call out a bunch of mistakes that I may have done in the video. Okay, yeah, that reminds me. Last time somebody asked me, how do you usually give hiring recommendations? So for this problem, I would say a candidate should get hired if they either come up with this order and algorithm that we discussed, the non-greedy one, where you iterate through all the prefixes and perfectly code it up without any bugs, that is. For the greedy approach, I would say this rigorous proof is not important. As long as you cover all the corner cases and provide some intuitive arguments about why this approach is right, it can work. If you really can provide, some theoretical arguments, that would be really amazing. Yeah, and the intuitive arguments again would still go into these directions that I mentioned. All right, so that's it.